Now, after we've heard so much interesting information about sensors and also lots about controls yesterday, we come to the third main part of active control technology, which is the actuator. This presentation here consists of two parts. Skip that. Two lectures on actuators. I will do the first part, and after that, Hugo Pförtner will do the second one. I will concentrate on the generic actuation principles. I'll give you a short introduction again, then basic actuation principles, followed by some comments about how to do the technology choice for specific actuators. Then some generic requirements concerning actuators, and an interesting part, I hope, will be the emerging technologies for new actuation systems. So again, as an introduction, I would like to show you the performance limitations we have currently in aircraft engines. Maybe you remember some of them from my presentation yesterday. We've got inlet separation, we've got stall and surge in the compressors, combustor instabilities, afterburner instabilities, noise, and all that what's associated with that. Tip clearance problems, distortions, and flutter and vibration problems. So now we're trying to modify these physical processes by actuating, by actively modifying flow or mechanical vibration. Again, the control loop in active control, and we are here now in this part. So actuation, and actuation is a very important part of it, because you only can really modify the engine or component characteristic if you do it correctly, if you are on the right spot, if you do the right thing, and that's one of the main challenges here. Another important issue is that there's a lot of technology development going on. A lot of things have been explored, but there's still more to be done. More development is needed to drive the product to the next TRL level. So looking back in history, Frank Whittle, in fact, Frank Whittle and Oheim, they were the first to already control the engine simply by putting in fuel and having their valve for fuel control. Later on, by having larger engines, higher pressure ratios, and multiple stages, we saw that there's a need for control in the compressor section. So there were variable guidelines and feed valves applied in the 1950s. What we today have, the present here, is of course fuel input, variable guidelines and feed valves, but also first generation of tip clearance control systems. See these tubes here. We've got variables intakes and variable nozzles in military fighters. So we already are in the position to control the engine, but currently we can't speak of a smart control yet. So currently we have hydraulics, which are bulky systems for high forces. They weigh much, they are complex. Also electromechanical methods for the low force applications. But what we're looking for is these elements here. We want to reduce weight while keeping a very high reliability at low cost, and of course a very low environmental impact. Again, these systems have been demonstrated, so there are the basic principles available. But there's a lot of development required to drive these systems into a realistic engine environment. So here's some major three actuation principles And I will now go through that and show you how it is done. First one is flow manipulation. We've got microflow control on one hand side. On the other hand side, larger flows which are controlled for large-scale flow switching. Because here you don't only control, you really switch large amounts of flow, mass flow. And we've got the third point is mechanical manipulation, which are changes of geometry, morphing geometries, you could say. Sometimes a fairly simple process, sometimes really hard to handle. So let's start with microflow manipulation. Here's the basic problem we have in turbo machinery. You recall that we've got a machine with a working fluid. So we've got flows everywhere, and these flows have boundary layers on surfaces, and they tend to detach if there's a pressure gradient, an adverse pressure gradient, meaning that the pressure downstream is higher than the pressure upstream. So the flow detaches, which means that basically there's a boundary layer which thickens up and then detaches from the end wall. Now if you think of actuation, you've got the possibility to energize the boundary layer, to put momentum into it, to put energy into it, and therefore energize a low momentum fluid. Another technique would be to remove this low momentum material, so you suck it away, basically. And therefore, distributed sensing and actuation is needed because you've got to sense this physical process at the right place and then, of course, influence it where the detachment takes place. The consequences of these flow separations are very vast. It limits the maximum lift on airfoils, for example. It decreases drag, like in this example here, for an inlet with a distortion or an inlet separation. It produces drag and pressure losses, in fact, and it induces a certain degree of unsteadiness. And this will cause buffet and fatigue. And for compressors, of course, limits the stall and surge margin. So we've got all these problems involved with flow separations. And now we can look into control of these separations. And that's not a new topic, and I think you're already familiar with this picture. For anyone who plays golf should be familiar with that. That's the golf ball principle. So you have a ball, a smooth sphere here, and what happens is that the flow, the boundary layer, is laminar and detaches here and forms a very large wake, which then produces losses, and the ball won't fly very far. So there's the technique of putting dimples into the ball, small holes, which gives us a turbulent boundary layer. So state changes from laminar to turbulent, and a turbulent flow, a turbulent boundary layer attaches longer than a laminar one. And longer means also that the flow goes around the ball and the wake will be smaller afterwards, which then makes the ball fly wider, longer, and to aerospace, the transfer to aerospace would be that we have got lower losses. And enhanced lift, for example, for these wings. So in aerospace there are several means of turning the laminar boundary layer into a turbulent one. Like, for example, these vortex generators here on this wing. There's also some slots maybe where you can induce a certain amount of turbulence. I think that's shown here on the next slide. So that's still the ball here. see in this experiment the large wake. Now what you can also do, instead of turning the boundary layer turbulent, you can energize the boundary layer here in the wake. And that's done here by a jet with this yellow triangle, this position. There's a jet blowing out into the wake, which has been energized. And this makes the flow turn really around this ball and keeping, not really attached, but keeping a very low boundary layer. And so in the end, we will see a reduced wake. Okay, if you compare this distance with that one, therefore very low losses. In this experiment, this is done with a synthetic jet, which means, again, a blowing and a suction done at the same time, oscillating around the mean of 0. So net effect would be 0 mass loss.
Not a golf player. I don't know dynamics. So it's a basic question. On your first chart, you showed that you had separation that caused losses in the inlet of
this one?
compressor. Yes.
Mm-hmm.
So separation was not desirable, right? The concept of separation of layers is undesirable. But in the golf ball example, you actually induce disturbances, and you said that causes the boundary layer to actually adhere to the ball longer.
Mm-hmm. Exactly.
That part.
Okay. It's this part here. So what you do is you induce, or you turn the state of the boundary layer from laminar flow to turbulent one. Turbulent means that there's a flow not only going into one direction, but going in different directions, three-dimensionally. And so there's a movement between the outer flow and the very end wall, flow near to the end wall. And this enhances the energizing of the flow near the end wall. So that's why the turbulent flows keep to attach longer than laminar flows. In laminar flows here, there's a very low moment fluid which can evolve because basically there's nothing happening. So the laminar flow gets, the laminar boundary layer gets thicker and thicker and thicker, and just until it detaches. And if nothing happens, that's like or you could say that nature forms its shape itself.
You typically lose some energy due to the turbulence, but you gain a pressure recovery due to the better attachment of the flow. So it's a trade-off in introducing vorticity. The same is here with this vortex generator on the airfoil. They create an additional drag, but it's preferred against having a big separation. So
it's true, the losses here, the pressure losses in this part are higher than in this part. Okay. But the net effect is seen here in this way. And you could imagine with this wing, if you got the flow attaching and then you've got a certain turning of the flow, then you have got a higher lift. That's what you want to get.